Okay, hello and welcome back to Chemistry Talk. Today I'll be continuing kinetics and we'll be studying the kinetics of first order reactions. So in our previous video we learned how to determine order of a reaction, how to write the standard rate law, and a little bit about the concepts behind kinetics, but now we're going to put that all together and study the first order reactions of kinetics. So a couple things about first order. First order is the most common of the kinetic reactions. So that's just a fact that I thought I would throw in there. It's the most common. And it does have some useful examples in the real life world. This is how we study nuclear reactions. And this is also how pharmaceutical companies are able to determine the decay of drugs. Now, what I mean by decay of drugs is at what point will the drug be of no use anymore, where it's either lost its potency or it's not going to work. So the decay of drugs, and that is also known as shelf life. So, when will it expire, the drug? So it does have some useful applications. So when we're looking at first order reactions, we're looking at where the concentration of the reactant is at the first order power. So when we write the integrated rate equation, we need to include the natural log. It's just how first order reactions work. So there's two forms of the equation. The first one on the left is what you use most often. It is the natural log, or the ln of the concentration initially minus the ln of the concentration at a certain time specified, and that would equal the rate constant times the time. Or if you want to check your work or you have enough information, you could say that the ln of the initial concentration divided by the ln of the final concentration at that time equals kT. You don't want to use the second one when you're trying to find concentrations, because it does make the math a little bit worse. So also important to note that if you were to draw a graph, most oftentimes you will, of a first order reaction with time being on the x-axis and the ln of the concentration of the reactant on the y-axis, you would be looking at a linear relationship. So first order reactions have a linear relationship. Now, this idea of half-life has to do with how long would it take half of the sample to decompose. That has to do with the drug shelf life. So the formula for half-life of first order reactions is not too bad. The half-life equals 0.693 divided by the rate constant. The 0.693 comes from the ln of 2, or for half the sample to decompose, is 0.693. The reason why we can assume that it's always 0.693 is that concentration of reactants in first order reactions don't affect the half-life. So that's why we can simplify it to the half-life for the first order reactions equals 0.693 over K. This is not true for second order reactions. Okay, so I have a standard example problem here that we'll work through. The decomposition of hydrogen peroxide to water and oxygen is first order. Okay, so we know it's a first order, with a rate constant of 0.0410 inverse minutes at 25 degrees Celsius. So I ask three things. I ask, if the initial concentration of hydrogen peroxide is 0.05 molar, what will be the concentration after 655 seconds? I also ask, how long will it take for half the sample to decompose? So that's the half-life. And I also threw in an interesting problem. How long will it take for 1 pint of 3% hydrogen peroxide to decompose 99%? So that's a pretty hard problem, but we'll get to that at the end. So starting off, if the initial concentration of hydrogen peroxide is 0.05 molar, what will be the concentration after 655 seconds? So we're going to be using our integrated rate law equation, and that says that the natural log of the initial concentration of reactants minus the natural log of the final, or at the certain time, and in this case the time would be that 655 seconds, equals the rate constant times the time. What do we know? We know, let's change colors here. We know that the initial concentration of hydrogen peroxide is 0.05 molar, and that's this right here. We don't know the concentration at 655 seconds. That's what we're looking for. We do know the rate constant, and that is 0.041. And that's in inverse minutes. And we do know the time, which is 655 seconds. Now, there is a problem within the problem here, and that is a common thing that occurs. The rate constant's units don't match the time. So if you see here the rate constant's in inverse minutes, here the time is in seconds. So to work with inverse minutes and convert it to seconds is a little bit more annoying and difficult. So I'm going to take the seconds and convert it into minutes. So 655 seconds in minutes is 10.9 minutes. I just divided 655 by 60 because there's 60 seconds in 1 minute. So it's 10.9 minutes. So now we can solve for the concentration at 10.9 minutes. So the natural log of the initial concentration, 0.05 molar, minus the natural log of the time, or the final concentration at 10.9 minutes. Just put it in for T there. And that would equal the rate constant, K, 0.041 molar, times the time, 10.9 minutes. So what I am going to do here is find the natural log of 0.05 molar. So the natural log of, where's my calculator? The natural log of 0.05 molar is negative 2.99. I'm going to add that to the right side. So if I add 2.99 to the right side and multiply that by 0.041 molar times 10.9, I get 3.433. So what I did, once again, I didn't write out the steps because it would be a little bit tedious, but I took the ln of 0.05 molar, I moved it over to the right side, and I combined it with these numbers here, and I got 3.433. Now that equals the negative natural logarithm of the concentration final, or at the time we're looking for. So the math here gets a little bit interesting or tricky. So we've isolated our variable, and our variable, we have two problems. One is that it's a function. We need to find the inverse of that function. And two, it's negative. So the first thing I'm going to do here is eradicate this negative. So to eradicate the negative, I'm going to multiply everything by -1. Because we can have a negative number, but we can't have a negative function here. So now the ln of the concentration at the time would equal negative 3.433. So that took care of the first problem. Second problem is we need to find the inverse of this function to cancel it out. Now if you recall, the inverse of the natural logarithm is e. It's just an algebraic function. So to undo the natural logarithm here, I'm going to multiply both sides by e to the x. So what I get is that x would equal e to the negative 3.433 power, undoing the natural log. So now I get that my concentration, or my x here, at the time specified, the 10.9 minutes, equals 0.0320 molar. And that's the final answer, the concentration at that time specified. Now, if you notice, it makes sense because the concentration decreased from the initial concentration. It would make sense for the final concentration to be more. So the math does get a little bit confusing here if you're not good with your algebra, so just be careful in these algebraic steps. Okay, so how long will it take for half the sample to decompose? So that's half-life, and luckily half-life for first-order reactions isn't bad. It's the ln of half of the sample, like I said, 2 over k, but this can be simplified to 0.693 over k. That's a 9 there. So the half-life of this reaction would equal 0.693 over k, which is, in this case, 0.041 inverse minutes. So the half-life, the time for half the sample to decompose, is 16.9 minutes. It's that 0.693 divided by the rate constant. 0.693 divided by 0.041 molar is 16.9 minutes. Okay, finally, how long will it take for a 1 pint 3% hydrogen peroxide solution to decompose 99%? Okay, so this is interesting. This isn't more of an application problem. So here's what we know. We do know the concentrations initially. Now that's helpful because we can use the second form of the integrated rate law equation. And that was, if you remember, the natural log of the initial concentration over the final concentration at the time, and that equals kt. And here we're solving for t. So we can use this second form of the equation. But there is a problem. The problem is that I have a 3% hydrogen peroxide solution, 1 pint of it, but I need my concentrations to be in molarity. So I need to take this mass percent and put it into a molar percent. a molarity, a molar. So first thing I'm going to do is say that since it's a mass percent, 3 grams of hydrogen peroxide are present. It's a review of solutions over 100 grams of solution. Now the solution density here is 1, and we have 1 pint, so that would equal 0.100 liters. As far as the grams of peroxide go, the moles of peroxide go, because molarity equals moles of solute over liters of solution, to find the moles of hydrogen peroxide, I would take the 3 grams and divide it by the molar mass, which is 34. And I get the moles to be 0.088. Just did that in my head, just make sure that's correct. 3 divided by 34, 0.088. So my molarity would be 0.088 moles of peroxide divided by the 1 liter, the 0.1 liter is the solution. So the molarity of the solution is the 0.88 molar. So this is also my initial concentration of peroxide. My initial concentration of peroxide equals the 0.88 molar. But my final, well, the final would have to be when the 99% of the sample decomposes, because it says how long will it take for the 1 pint to decompose 99%. So another way of saying that is what is the concentration of the sample when 1% is left. And to do that, I would just take the 0.88 molar that I'm starting with and multiply it by 1%, or 1 over 100. And I get the sample that's left at that point is 0.0088 molar. Okay, so now that we've done the bulk of the work, all we need to do is just solve for T here. So T would equal the natural log of the initial concentration over the final concentration, and that will give us a numeric value, divided by the rate constant, and that would equal T. So the ln of 0.88 divided by 0.0088, and that will give us a numeric value, just remember that, over K, which is 0.041, will equal the time that it takes for 99% of the sample to decompose. So the natural log of 0.88 divided by 0.088 divided by 0.0410, that means that T will equal 100.
It's 3 o'clock.
T will equal 112.3 minutes. And that's the final answer. So this one was probably the hardest one. You needed to convert your sample into molarity. Then we could use the second form of the integrated rate law equation to solve for T. Hope this helped you to understand first order reactions. Leave comments below with any questions.